Hi everyone. Today in this class we will go through physical properties of carboxylic acids, right? And we have already done physical properties of many other organic compounds like alcohols, aldehydes and ketones, right? Haloalkanes, haloarenes. Now carboxylic acids, right? And we would be studying the same kind of similar physical properties like solubility, boiling point, melting point, right? And physical state, color, odor, these kind of things, right? So let's first quickly look at the physical state, right? Physical state, color and odor, right? First three members, right? Formic acid, acetic acid, propanoic acid, right? So C1 to C3, these are pungent smelling liquids, right? These are pungent smelling colorless liquids, right? Now for C5 to C9, from C4 means butyric acid, right? From C4 to C9, I'm sorry. These are goat, the smell is unpleasant goat-like odor, right? And these are colorless oily liquids, right? These are pungent smelling colorless liquids and these are colorless oily liquids. Remember, these are the first three are not oily, whereas the C4 to C5, these are colorless oily liquids, right? And if we talk about odor, it possesses unpleasant odor, unpleasant to be correct, goat like odor, right? Now C10 and above, these are colorless waxy solids, no odor. Why no odor? Maybe possibly because they are not volatile, right? Because they cannot vaporize, so there is no smell, right? So this is about the physical properties, right? And if we talk about aromatic acids, parent acid of aromatic acids we know is benzoic acid. So almost all aromatic acids, benzoic acid and higher acids, all are colorless solids, right? Benzoic acid and other aromatic acids, right, are colorless solids, right? This is important, they are solids at room temperature. Now there is a reason for why all aromatic acids are solids. The reason is that the aromatic acid, like this, all these aromatic acid has this planar ring, right? Since it is planar, it's planar, it's plain ring, due to which its packing in the crystal lattice is of high efficiency. It's in short, we say that due to this planar ring, aromatic acids are well packed in the crystal lattice. Since they are well packed, due to their well packing, the force of attraction between different molecules is high, or what we say is intermolecular force of attraction between benzoic acid or between aromatic acids is high, right? And why it's well packed? Because of this planar ring, right? Because of this planarity, benzoic acid is well packed, right? Due to which intermolecular force of attraction is high, and that is why aromatic acids are solids at room temperature, right? Solid at room temperature. This is due to planar ring that makes its packing efficiency high in lattice, right? Or what we say is it's well packed in its crystal lattice, due to which its intermolecular force of attraction is high, right? That is why all aromatic acids are solids at room temperature. Right, now let's look into another important property, physical property, which is solubility in water and inorganic solvents. Right, we know one rule, like dissolves like, right? So we know that organic compounds are less polar, right? And organic solvents are also of same nature, right? Either they are non-polar or less polar. So that is why carboxylic acids and other aliphatic acids and aromatic acids are soluble in organic solvents, because of their less polar or non-polar nature, right? Because of this, or what we say is because of similar nature of carboxylic acids and organic solvents, they are soluble in water. Now let's talk about the solubility of carboxylic acids in water, right? In water, if you remember, alcohols are soluble in water. Why? We have done this before, because they can form hydrogen bonding with water. So if you want an organic compound to be soluble in water, it should be able to interact with water, right? Now interaction means there should be some force of attraction between the molecules of solute, which is your carboxylic acid here, and the solvent, which is water. So in case of carboxylic acids also, carboxylic acids would be able to form hydrogen bonds with water, right? And in carboxylic acids we have like this. You have we know that for hydrogen bonding we need one electronegative atom, and the other atom should be hydrogen. So in carboxylic acid you can see we have hydrogen. This hydrogen can form hydrogen bond. This hydrogen can form hydrogen bond with highly electronegative oxygen atom of water molecule, and oxygen atom of carboxyl group can form hydrogen bonding with hydrogen atom of water molecule, right? Similarly, this water molecule can now form hydrogen bonding with hydrogen atom, carbon with hydrogen atom of carboxylic acid molecules, and this oxygen of carboxylic group can form again hydrogen bonding with hydrogen atom of water molecule, right? So we have hydrogen bonding. Through hydrogen bonding, carboxylic acids can interact with water, right? So that is why carboxylic acids are soluble in water, but it's only lower members that are soluble in water. As you keep moving up, right, as the molecular mass increases, the solubility in water decreases. Now what determines the solubility? The other thing, if you know, this is your carboxylic acid, right? RCOOH. Now this R is your hydrophobic part, alkyl group. This is your hydrophobic part, which is insoluble in water, or which is water hating. This is hydrophobic part, right, which is water hating, right? Now in lower acids like formic acid, acetic acid, propanoic acid, the R group, the size of R group is such that the hydrogen bonding, right, the size of this R group is such that hydrogen bonds that are formed between carboxylic acid and water can hold these carboxylic acid molecules together in water. But as the size of this R group, as the size of this alkyl group increases, this is the alkyl group, as the size of alkyl group increases, its solubility decreases. Why? Because this alkyl group is insoluble in water, right? And when this alkyl group, the size of the alkyl group increases, then this will dominate, right? Or what we say is, when the size of the alkyl group increases, these these hydrogen bonds could not hold this carboxylic acid molecule in water, right? These hydrogen bonds would not be able to hold these carboxylic acid molecules because of this bigger hydrophobic alkyl group, right? I hope this is clear. So the question that might come is, why higher carboxylic acids are insoluble in water? Because of this growing alkyl group, which is hydrophobic, insoluble in water. Due to this bigger alkyl group, right, these hydrogen bonds would not be able to hold these carboxylic acid molecules together, right? And as a general rule for any organic compounds, alkyl group will always be hydrophobic, right? It would be water insoluble. So as this group keeps on increasing, as its size keeps on increasing, its solubility in water will decrease. Why? Because this alkyl group would not be able to form, or this alkyl group does not form hydrogen bonding with water. It's only the other part, this carboxylic part, that is forming hydrogen bonding in water, right? But as the molecular mass increases, the carboxylic group will remain same. It's only the alkyl part that will grow, which is water insoluble. Now when it will keep growing, it will make the entire carboxylic acid insoluble in water, right? I hope this is clear. Now let's look into the other important property, which is your boiling point. Boiling point, right? Boiling point, if we talk about boiling point of carboxylic acids, is greater than boiling point of hydroxyl, that is alcohols, and boiling points of hydrocarbons, right? Let's first understand why boiling point of carboxylic acids is higher than that of water, right? Let's first look into its structure. Right? This is your negative oxygen and this is your hydrogen. Why this is negative? Because of high electronegativity of oxygen. This is negative, right? Now what will happen is, since we know that boiling point of alcohols are higher because they can form hydrogen bonds, right? This OH, right? This OH, if you remember, this is your ROH. Right? This alcohol molecules can form hydrogen bonds, right? These alcohol molecules, OH, these alcohol molecules can form hydrogen bonds between one another through hydrogen atom of this OH group and oxygen atom of this OH group. Basically, this is your intermolecular hydrogen bonding, where one molecule of alcohol is forming hydrogen bond with another molecule of alcohol, right? And it is due to this OH group that alcohol molecule can form hydrogen bonding between one another, right? I repeat, it is due to this OH group, you can see, right, that alcohol molecule can form hydrogen bonds between one another, right? So since alcohol molecules now have one additional force, right, that is acting between molecules, that additional force is this additional force is this hydrogen bond, right? But in alkanes like methane, we have only hydrogen atoms. There is no electronegative oxygen atom, because for hydrogen bonding to exist, we need one highly electronegative atom like oxygen, nitrogen, and other hydrogen atom. Here we have only hydrogen atom, right, and only carbon atom. We have no electronegative atom. So there is no hydrogen bonding in hydrocarbons, right? Hydrogen bonding exists only in alcohols. Similarly, if we talk about carboxylic acids, right, like this, right? This is one molecule of carboxylic acid. This is another molecule of carboxylic acid, right? This is basically, these are two carboxylic acid molecules that are associated via hydrogen bonding. You can see this is a hydrogen bond between hydrogen of one molecule and oxygen of another molecule. Similarly, this is also hydrogen bond between hydrogen of one and oxygen of other carboxylic acid molecule, right? So due to this, these carboxylic acid molecules are associated with one another, right? These are associated with one another. Now this is actually a dimer. Here two molecules are joined to one another. This is a cyclic dimer, right? So if this is acetic acid, this is an acetic acid molecule dimer, right? So carboxylic acid molecules exist as dimers, right? Remember, because this is also responsible for its higher boiling point. Now the question is, one thing we understood, that here in carboxylic acids we have hydrogen bonding. In hydrocarbons like methane, ethane, we don't have hydrogen bonding because we don't have any electronegative atom like oxygen, nitrogen, right? Due to which these hydrocarbons can form hydrogen bonding between one another. But in carboxylic acid and in alcohols, we have highly electronegative oxygen atom and hydrogen atom. So these can form hydrogen bonds. So we say that boiling point of carboxylic acids and alcohols is higher compared to these hydrocarbons, right? Due to hydrogen bonding, simple. Right now, the other thing that we need to look into is that why the boiling point of carboxylic acid, right, is higher than alcohols, right? Why this is higher than alcohols? We know why it is higher than hydrocarbons. Now we'll see why it is higher than alcohols. If you look at carboxylic acid, this is your carboxylic acid, right, in which this carboxylic acid, this is electron withdrawing group. This is electron withdrawing group, right? Due to which, since this is electron withdrawing group, it will withdraw electrons towards itself. Because the main thing is, because we have highly electronegative oxygen atom here, it has high electronegativity, so it will withdraw electron towards itself. So basically this carbonyl group is electron withdrawing, we say, right? And this carbonyl molecule, because it is electron withdrawing, so it will make this OH bond highly polar. Basically the polarity of OH is more, right? The polarity of OH is more in carboxylic acids as compared to in alcohols. If you look at these alcohols, this R group is not electron withdrawing, right? This R group is not electron withdrawing, so it cannot make this OH group, it cannot basically increase the polarity of this OH group, right? On the other hand, this is electron repelling, right, or electron donating, whereas carboxylic group is electron withdrawing, right? So it will make this OH bond strongly polarized, or what we say is it will make this OH bond more polar compared to OH bond of alcohols, right? And since this is more polar, so it will form stronger hydrogen bonds, right? Since OH bond in carboxylic acids is more polar, which makes OH bond since OH bond in carboxylic is more polar, which makes stronger hydrogen bonds between your carboxylic acids, right? More polarity means more stronger hydrogen bonds, right? Just understand that. So this is the reason why carboxylic acids have higher boiling points than alcohols, right? Simple reason, because carboxylic acids can form stronger hydrogen bonds than alcohols. Why they can form stronger hydrogen bonds? Because carbonyl group which is attached to OH group in carboxyl group is electron withdrawing. So it will withdraw electrons and will make this OH bond more polar compared to OH bond of alcohols, right? That will make hydrogen bonds in carboxylic acids stronger, right, compared to in alcohols, right? I hope this is clear. Now let's quickly look at, and the other thing is, since this carboxylic acids exist as dimers, so that is the reason that is also one of the reasons that these carboxylic acid boiling points is higher, right? So I'll just write it over here. Since these exist as dimers, right, that makes its boiling point higher, right? I hope this is clear. And this dimer state, this is confirmed. If you remember, we have done colligative properties in solution, right? And this colligative properties of carboxylic acid comes under abnormal colligative properties. When we say abnormal colligative properties, it means if you add benzene molecule in benzene, say you add acetic acid in benzene, the molecular weight, right, of carboxylic acid is double in benzene. Why? Because in benzene, through hydrogen bonding, right, the carboxylic acid molecules dimerizes, right? That is, they combine through hydrogen bonding into and change into a dimer. That is, it dimerizes in benzene solvent, right? That is why it shows a higher molecular weight or molecular mass in benzene solvent, right? So this also adds to the high boiling point of alcohols, carboxylic acids, right? Now let's look into another property, which is your melting point. We say that melting point of these acids is higher, right? We say that melting point of carboxylic acids that contain even number of carbon atoms is higher than odd number of carbon atoms, right? So what it means is, if we have a carboxylic acid with 2 carbon atoms, which is an even number, right? The boiling point of carboxylic acid that has 2 carbon atoms, CH3COOH, right? After this, the acid that will come, it is CH3CH2COOH. Before this is HCOOH, right? So here you have 1, here you have 2, here you have 3, right? So melting point for carboxylic acid that contains even number of carbon atoms is higher than its immediate neighbors that contains odd number of carbon atoms, right? So these are its immediate neighbors, formic acid and propanoic acid. So melting point of acetic acid would be higher than formic acid and propanoic acid, right? We'll look into the reason based on its structure, the structure of acids that contains even number of carbon atoms, right? So, and we also say that melting point of aromatic acids is higher than aliphatic acids. We'll look into the reason why, right? And one more thing, this entire thing where the where the melting point of even number of melting point of carboxylic acids that contain even number of carbon atom is higher, we call this effect as oscillating effect, right? And there is no regular trend in the melting point of carboxylic acids, it shows this kind of oscillating effect, right, where this carboxylic acid has higher melting point than its lower member and its higher member, right? So there is no regular trend. This is an oscillating thing. This is an oscillating effect, right? So the melting point, we say melting point of carboxylic acids vary in oscillating fashion. It varies in oscillating fashion. Now we know what is oscillating fashion, right? Now let's look at the structure of a carboxylic acid that contains even number of carbon atoms, right? This one, right? The other is CH3, CH2, 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 then you have COOH. There are 2, 3, 4. This has 4 carbon atoms, even number. Now 1, 2, 3, 4, 5. This has 5 carbon atoms. This is your odd number, right? So as per this rule, the one that we have done, the melting point for this one should be higher than this one. Why? If you look at this acid, if you look at the terminal groups, the methyl group and COOH group, these are on opposite sides in case of acids that contain even number of carbon atoms, right? Whereas the terminal groups are on the opposites, are on the same side. Terminal groups, these are terminal groups. These are on the same side of those carboxylic acids that contain odd number of carbon atoms, right? Now melting point, basically melting point is, now this is clear. Now when we say melting point is higher or lower, melting point is basically depends on how molecules are packed in a crystal lattice, right? How molecules are packed, right, in the crystal lattice, right? So the molecules that have even number of carbon atoms, or molecules that have terminal groups facing one another, terminal groups on opposite side, right, are well packed, right? These carboxylic acids that have terminal groups on the opposite side, these are well packed, right? And these carboxylic acids that have terminal groups on the opposite side, terminal groups on the same side. You can see methyl group and this are on the same side. These are less tightly packed. These are less tightly packed, right? Now if these are well packed and these are less tightly packed, obviously the molecules that are less tightly packed tightly packed, they have less force of attraction, right? Since they have less force of attraction, so you need to give them less energy in order to separate, or in order to make their molecules move apart. When the molecules will move apart, it will melt, right? So here these molecules are less tightly packed, right? So you give them less energy to separate. Since you give them less energy to separate, their melting point is low, right? Now if you look at this, these are well packed, right? So you have to give them high energy, right? Since you give them high energy in order to separate their molecules, because due to well packing, there is high force of attraction between the molecules, right? So high energy means high melting point, right? I hope this is clear, right? Due to which this is well packed. Now coming on to aromatic acids. Aromatic acids are well packed because of the planar ring, right? They have this planar ring because this ring is planar. These aromatic acids, all aromatic acids are well packed, right? Since these are well packed, their molecules